We'd like to especially extend a warm welcome to Arianna Bisazza from the University of Groningen. And so just to give a brief introduction before Arianna begins her talk, she's an assistant professor in computational linguistics at the University of Groningen, the Netherlands. Her research aims to identify the intrinsic limitations of current language modeling paradigms and to improve the quality of machine translation for challenging language pairs. She obtained her PhD in statistical machine translation from FBK University of Trento in 2013 and has been recently awarded a large national research grant on interpreting deep learning models for text and sound as part of the InDeep consortium. So without further ado, we'd like to turn the time over to Dr. Bisazza, and we look forward to hearing what she has to say and interacting with her.
So, hi everyone. Can you hear me well? And does the chat work? So, yes, I guess everybody has access to the chat, right? So, welcome to my talk. I would really like for this to be as interactive as possible, so please do not hesitate to post your question to the chat. Does the chat work? I haven't seen any message yet.
Should work.
It should work, right?
Should
or
work.
Of course, just raise your hand, whatever works, chat or talking. So also thanks, Devin, for the nice introduction. I had actually prepared a very brief introduction myself, but yes, it's not needed anymore. So if you're wondering where Groningen is located, this is where I am talking to you from right now. And I think there's quite a bit of people from Europe, actually. It's quite surprising. And although, yeah, Devin already said quite a bit about myself, these are my research interests. Broadly speaking, computational linguistics and natural language processing. I've done quite a lot of work on machine translation, but I'm interested also on morphology and models that can language more, models that can model more than a language simultaneously. And also more related to the talk to today, deep learning methods for natural language processing. I've done my PhD in statistical machine translation. That was before the advent of recent neural approaches to MT. And actually, I just wanted to share that my undergrads were in something totally different. So I don't have an actual human translation background myself, but I studied Oriental languages in my undergrad. So I have a kind of a mixed background, and I've been fascinated by learning new languages and understanding how translation works and how we can model it for a very long time. And I actually know Michael from quite a long time ago. During my PhD, I was at a summer school in translation processes while he was still working at Copenhagen, I believe. Correct me if I'm wrong, Michael. So I'm actually here today to talk to you about the problem of interpretability in deep learning models of language processing, and more specifically of machine translation. And I will try to make my talk as accessible as possible to a large audience. And I really designed my talk with this audience in mind, hoping that we can really have a discussion and you can help me to come up with interesting questions for the project that we have just recently started. So I repeat it again, please do not hesitate to ask questions. I really like people interrupting me during the talk. And I have a little disclaimer. This talk will include lots of questions and only a few answers. Yeah, mainly because we are still in the beginning stage of this project, and also because I chose to focus more on this part of the content, because I think it's the one most relevant to you. So now let me get started. By the way, I'm curious, is there anybody from the machine translation world here, or is mostly people working on human translation processes, if I may ask?
I believe from what I see, some people are from the MT community, but only very few. But
Okay. So it's mostly people working in your group on the study of the human translation process, correct?
Well, or from all over the world.
Yeah, okay. Yeah, there is a raised hand. Ah, okay. Thanks for creating the poll. Very useful. So in the meantime, I can continue. Ah, no, I cannot move to the next slide unless I close the poll for some reason. Maybe I can.
Okay, I'll show the replies from the poll
Thank
really
you.
quick and then close it.
Yeah, focus on, it's already very useful. But yeah, there's at least 4 people from the MT community, so that's interesting. So, well, a brief introduction on the problem of today. We all know that machine translation is part of the daily workflow for a very fast increasing number of professional translators. And actually, this plot is from a recent report from MIMSI about the top 100 largest language service providers, where they show that machine translation and post-editing was the second most offered type of service offered by the second largest number of service providers. And these numbers are increasing quite fast as we speak. Also, to give a bit of a larger context of where we are going to talk about. So we are interested in how the machine translation, not just how it performs, but also how it impacts the experience and the workflow of the human translator, which we can call a post-editor. I am just seeing if I have the cursor here, but I'm afraid I don't with the new collab version. Okay, I'll try to do without it. So there's a rather complex machinery that's behind the scenes of a modern translation interface, and machine translation plays an increasingly important part in this interface. So we'll zoom in here and first try to understand how MT works in 2021. And although exceptions exist, I think it's safe to say that most language providers nowadays have switched to neural machine translation technology, which relies on an artificial neural network trained on large amounts of translated data to mimic human translation. So it's a machine learning model, and more specifically using neural networks. We'll see soon what that means, later what that means. It is fully data-driven, just like pre-neural approaches that were relying on, for instance, phrase-based machine translation. However, it differs from it in many ways, and from the point of view of the users and the developers, what matters is that the quality that it delivers is much better overall. At the same time, so that's on the good side. On the negative sides, we have a model that is much less interpretable. It's much less prone to understanding why it makes certain decisions or not. So let's take a step back first and try to understand what an MT is really for the people that are not MT. If you are in MT, this will be a bit redundant for you, but I believe that it's important to bring everyone on the same page before I can explain my work. So very, very brief history of neural networks. This is stuff that has been around for quite a long time, ever since the 40s, when the McCulloch-Pitts neuron was introduced as a simplified model of the human neuron. Since then, it has taken quite a while to arrive to the models that we're using today because there were several issues. And during two phases, the revival in the 80s, when the propagation and other techniques made it possible to build complex and deeper networks with many layers. Then with what has been called the deep learning revolution in the 2000s, further improvements in optimization techniques and also very importantly, computer hardware improvements have enabled neural networks to finally scale up to real-world AI tasks. So the idea of an artificial neural network is not new, but it took a very long time to make it really functional and production ready. And what's important to remember and to know, if someone doesn't really know what a neural network is that it's not really the model of a brain, although the name could suggest that. It's actually more looking like a graph, a connected graph. And the reason that this name has stuck around is that this is really something that has been called the brain-inspired metaphor, because the human brain is also a very large and complex network of simple units. So we don't claim any, although there's people that are actually working on the cognitive plausibility of these models. When we talk about a neural network, we don't mean to say that we are modeling the brain in any way, at least not in this talk. We mean it as a branch of machine learning. Are there any questions so far? Okay, if not, I move on. Otherwise, feel free to post your question on the chat. So what's interesting to know about neural networks is that they can be arbitrarily. Actually, making a network more complex is a key to make it work on complex tasks. So first, I'll try to give you, in a really gist, I will try to give you an idea of what a simplest form of a neural network is. So this is the feed-forward neural network with one hidden layer. And I will also try to give you the intuition of how this is used in a very simple example. So translation is, of course, not the simplest task that we can think of, but we can think of a slightly simpler task, which is that of classifying short phrases like the blue chair into two categories, verb phrase or noun phrase. You can think of many other tasks of this kind, but just pick this one for an example. And what's going to happen is that we will have these neurons. So each of these round here is what is called a neuron, or the simplest computational unit in the network. We have an input for each word. Okay, you can see it here. And this will be projected to this hidden layer whose task is to somehow infer features about the input. And then from this hidden layer, we'll arrive at the output layer, which in this case has two output units corresponding to the two possible output classes. Now, how is this actually used to learn something from data? Again, just to give you the intuition, sorry, I think I skipped a slide. So what we are going to do, we are going to ask the model to make a first prediction, which could be completely random because all of these units are randomly initialized. Okay, and they just contain numbers. So I'm so sorry that I cannot use the cursor. This function has been removed very recently. So we're going to ask the model to make a prediction, and let's say that in the first stage, the model could just predict that this was a verb phrase because it doesn't have inferred any knowledge from the data yet. Then we'll use the error signal contained in the data. So assuming we have a large data that for each phrase tells us what was the correct label, we'll use this error signal to update the model weights, which are here represented by these arrows. and they really are the knowledge that the model has. And then we'll use the updated model weights to make a new prediction, a refined prediction, which after a while, if you're doing the things correctly and if our training data is informative enough, will lead to the optimal predictions that are on average correct very often. Someone is asking, am I supposed to see your screen? Yeah.
You should be able to see the
cursor
presentation that she's sharing, yeah.
Oh yes, definitely. The only thing you cannot see is my mouse, unfortunately, but I don't think there's a way to show it. Yeah, I hope everybody else sees my slide, right? Otherwise you have a problem.
I can see your slides.
Okay, perfect. So where were we? So yeah, this is very speaking very intuitively. This is the framework of how a neural network is trained and learns from data. Okay. Now this is, as I said, the simplest form of feed-forward neural network, and the networks that we are using to solve machine translation or other real tasks are much more complex than that. How do we get to complex networks? In reality, building blocks are surprisingly simple. So there are only a few building blocks that, just like Legos, are combined to get to very complex networks. So we can add layers, we can add subnetworks, we can add special mechanisms or layers like attention layers, and get to very to increasingly complex architecture and networks. So it's not the goal of this presentation to really go into detail in these very complicated models. Again, I will try to give you the intuition of how a specific architecture that is used by the large majority of machine translation models nowadays works. Okay, and this architecture is called the transformer neural network. So the way this works is first we start always with a sequence, and we want to output the sequence, right? So this is not classification anymore. We're going from a sequence, which is the words in the source language, to another sequence, which is the words in the target language, could also be of a different length. And we have two important components: the encoder, which is tasked to predict the input sentence to representation that the neural network makes sense of. Typically, it's just a bunch of real numbers. And then we have the decoder, which, starting from that representation, will generate a sentence in the target language. So let's start with the encoder. Here we see various things happening. Each word is going to be projected again to a word level representation, also called input word embedding. And then here we have encoding layers. I only drew two here, but there can be more. And using this really powerful mechanism of self-attention, I will don't have really time to explain how this works, but it's just a different type of neural network layer. This encoder is going to generate increasingly, how can I say, is going to increase, is going to generate different layers of representation that encode, it has been shown, more and more complex linguistic information. And once it has arrived to this last layer, it's now time to show what the decoder does with that. So the decoder is something that works pretty similar, whereas we have a component for representing the word by word. That's the word embedding. And this, for a start, is just a tag that means beginning of sentence. And the difference from the decoder, between the decoder and the encoder, is that the decoder is also informed by the encoder, which you can see with these arrows, right? And these are really important because this is what makes the difference between just a language model, so a model that's trying to predict the next word, and a model that is also conditioned on the source language. Okay, so one way to see this architecture is language model, so a model that tries to predict the next word in the target language, but being conditioned on the source language sentence, which is really what we need for translation, right? Again, we are using this mechanism of self-attention to generate increasingly complex representations. And at the end of this process, the model will output a distribution or a probability over the whole vocabulary. So what I try to depict here is basically a long set of scores where each word in the vocabulary, in this case, my example is going from English to Italian. Each Italian word will be associated with a score, with a probability. And when it's time to actually translate, so we are not training, but we are generating a translation, we are in production, let's say, what the model will do, it will pick one word that had a very high score. For instance, it could pick the word with the highest score. And it puts it there and says, okay, this is the first word in my target sentence. Then we can repeat this process for the second time step. And you can notice that now the word that was the first word that we generated, la, is now plugged here. And it is used as an additional context to generate the second word. So the second word, which is produced in the same way, is now conditioned on everything that came before in the target sentence and also on the whole source sentence. Okay? So we can do this repeatedly, and at the end of our time steps, we'll have generated a translation that's hopefully a faithful way to convey the source sentence meaning. And the way this can be trained is, again, intuitively very similar to what I just showed you, how we train a simple classification model. Of course, here training is going to be computational and more expensive, but the idea is really the same. So we start from a large corpus of parallel sentences, and we use them to get an error signal that we use to update the weights, which are again represented by all these arrows, and get in iterative procedure better and better versions of the model. So it's important to know that, I think many of you know that, but just to remind ourselves that Google Translate, as an example of an important online machine translation provider, has been powered by neural networks since 2016. So it has been now 5 years. And the transformer in particular, transformer architecture, is now the architecture that is used by most machine translation providers out there. I was really looking for some statistic, but it's very hard to get at that. But I'm quite confident that many providers have switched to transformers because it has been shown to be superior to the first types of machine translation architectures. Is there any question on this part? Because I think it's quite important that everybody has followed until here in order to make best use of the rest of the talk. Yes, I should take it as a yes. So you might be wondering, what are these rectangles? And that's the whole reason we are here, because I could say that nobody really knows. So, well, we do know what they are. They are vectors of real numbers. So each of these rectangles, if you open it up, what you'll see is a vector, or you can just think of it as a set of numbers with a fixed size. So if we have decided that the green rectangle should be 300 should have the size of 300, each of these green rectangle will contain 300 real numbers. And the purple rectangles, if we had defined them to also be 300 of size 300, it will also include 300 real numbers. Okay, great. But what do these numbers mean? Really, this is an open question. We know the mathematics behind it, we know the mechanics, we know how the model is updating these numbers. But it's a whole other story to make sense of them, to make human sense of them, and to say what each of these numbers mean, how it relates to the word that this number is trying to represent, right? So. Another issue that's that's another issue that regards this model is that they are less interpretable because they don't. If we compare them to pre-neural statistical machine translation models, they lack a whole set of components that made it still possible to somehow make sense of pre-neural methods. So the first component that is missing is a bilingual lexicon. Something that, if you're familiar with phrase-based statistical machine translation, could have been a phrase table. So there is no phrase table or no word-to-word translation table in the neural machine translation model. And I'm even saying not even a probabilistic one, not even a list of words with the probability of being correspondent to another word in a target language. We don't have that here. Secondly, there are no translation rules to be inspected, not even probabilistic ones. And thirdly, there are no separate components for meaning transfer and target fluency. So this, at least in phrase-based statistical machine translation, we could at least separate these two components of the model, the one that was tasked to transfer the meaning, and the other one that was modeling fluency or grammaticality, well-formedness on the target language side, which was the language model. So it's true that we have an encoder and decoder, but they cannot be decoupled as easily in the analysis as a phrase table and language model could be decoupled in these earlier approaches. So this has led to a really big problem in NLP and more general in artificial intelligence, which is the black box problem. Has anybody heard about the black box problem or about the problem of the goal of explainable AI? Seems that everybody is very shy to intervene. Wait a little bit more.
Yes, I've heard about it, but I'm curious to hear more about it.
Okay, in which context have you heard about it? MT or more general AI?
Well, generally for neural networks, that in fact everything happening in the hidden layers is a black box essentially.
Yeah. Okay. Good. Yeah. So this is precisely what this research of mine is about, and for the brain, of course. What do you mean? And how to explain the brain? Yeah.
Yeah, for many processes related to neural, not networks, but to neural problems, the brain is referred to a black box in translation, for example, things that we don't know what is happening.
Yeah, this is quite interesting because it is now a common criticism of people studying cognitive processes with neural networks that we are attacking a black box with another black box. Actually.
Exactly.
Yes.
Well, we all do that, right?
Yes, exactly. Yeah, thanks for your reactions, by the way. Please keep posting stuff in general AI topics. Yeah, so I think if you haven't heard about it in a strictly MT or NLP context, you might have heard in general news about AI because this is really a big hype. Yeah. So that was, I was curious about hearing what you have heard about it. So to me, the black box problem can be phrased like this. It is the fact that we have this learned representation, which, as I said, are just table of numbers. And these representations can be shown to have very interesting properties. I will give an example right now. However, if we take a specific dimension or a specific number, let's say the third number in the vectors, we cannot really say what it stands for. Okay. So first, what are properties? An example of properties is that we can represent, we can depict this vectorial representation of words in a Cartesian space, in a geometrical space, which will have a lot of dimensions, but for simplicity, let's just think of a space with 3 dimensions where we can place a vector is a point, sorry, each vector representing a word is a point in the space. And then if we look at the space, we will notice that the representation of cat and dog might be close to each other. The representation of dolphin might be a little bit further apart. And then if we look at the representation of spoon and airplane, these will be much further apart. Then something that is a bit more impressive, I would say, is the fact that we can also study the relationship between these points in space, between these vectors, and we could, for instance, notice that not just the distance, but also the relative position of kitten to cat is very similar to the relative position of puppy to dog. So this means that semantic relations, but actually also syntactic relations, or morphological ones, if the model has been trained properly, they will be reflected in the space. And we can even make mathematical operations over these vectors and find that it matches the linguistic intuition. I will read this question in a moment. I just want to finish this. So again, what I just said is that if you take, again, really look at the representation of, for instance, airplane, you have all these numbers and you still have no idea what the first mean, what the second mean, and what the third mean. This is, people are trying to do that and we are getting closer to the answer, but it remains something really hard to do. We can also reason in terms of sentence level representations, because that's also what we have there. And this becomes even harder to make sense of this, because we could have George Washington was the first president of the United States, leads to this set of numbers, and beat eggs, salt, and pepper in a small bowl until blending leads to another set of numbers. So what to do from there is really tough to figure. And so these are the problems, or these some of the problems. How the model is solving a task remains really unclear. Secondly, and more practically perhaps, if you find that your model makes an incorrect prediction or picks a wrong translation choice, it's hard to explain why. And as a result, it's also hard to fix these errors, and it's also hard to fix biases of different kinds, racial biases, gender biases, or other types in these models. I will now read the question by Devin. About 2 years ago, my yeah, so this is a very good point. From what I understand, the only way we have of interacting with the neural network model is through the training data that we give it. I think there's a lot of truth to this statement, although I do think that in the last years we have made some progress towards better interpreting and explaining neural networks. So at least in the direction going from the model to our understanding, I think there has been some progress. In the other direction, yeah, it's still quite hard to figure out. So how can we inject our, for instance, our domain knowledge into the model that's also very hard to figure. And it's true that the way, most of the way this is currently done is through some form of change in the training data. For instance, data augmentation is one of it. But yeah, it's really a problem. At the same time, it's a bit unlikely to think that these models will be dismissed. Some people are arguing for it, but they work so much better. So is it really worth throwing them away because they are not interpretable? In the end, like someone said, our brain is also a black box, but we don't want to renounce to it. So maybe maybe it's worth spending more time in trying to understand better how we can get more insight in these models. But thanks for the interesting remark. So what I wanted to say is that a lot of people have directed their attention on this problem in the last years, and this actually has given rise to a new field of research, which is called neural model interpretability, or also explainable NLP. These two terms, they don't exactly mean the same thing. There is also not clear how they differ, but they are often used interchangeably. So explainable neural models or interpretability. So there are now workshops and conferences about explainable AI. This is a workshop in the NeurIPS, the biggest conference about deep learning. We also have our NLP specific workshop for analyzing and interpreting neural networks for NLP. This workshop has started in 2018, and the last edition, which I just recently attended, was the biggest workshop of the whole EM-NLP. So it's really, really crazy how much attention this is attracting in the community. And there are also more and more implementations of interpretability techniques, tutorials, and so on and so forth. More and more people start to actually get their hands on these tools. But it's by no far a technology that is ready for production. There's a lot of stuff that still needs to be figured out. So there are many questions that fall within this this field. Some important questions, at least that are interesting, are the following. So what are source of linguistic information that are used by a model to make a specific decision? And secondly, are neural models sensitive to given syntactic phenomena? For instance, are they able to predict the subject-verb agreement in English, even in very complex sentences where you really need to figure out which one is the subject to know what the verb number should be? So I will now delve more into my own research part, which I divided into two parts. And the first one is ask whether neural machine translation models translate even vaguely like people. And more specifically, what we asked here was whether NMT models can extract linguistic features from raw text data and whether they can use them in explicable ways. Okay, it was a joint work with a student of mine. Specifically, we looked at morphological features in neural MT representations and asked a question of this kind: does the model know that a noun or an adjective is singular and feminine? And does the model know that the verb is in the past tense, for instance? And how we did that, we actually use another but simpler machine learning classifier to try to predict this information from the vectors that are generated by the neural MT encoders. And this gives us, if this simpler classifier succeeds, that's an indication that this information is actually learned and encoded by the neural MT model. Okay. So going back to the scheme of this translation system or architecture that I showed you before, what you would do basically is feed in these vectors to a linear classifier that's going to predict whether this word was singular or plural. The languages we worked on the language pairs were French to Italian, French to German, and French to English, because we were interested in seeing how the learning of French grammatical features would vary when we change the target language. So it's the same data from Europal corpus, but we vary the target language every time. And I'll just jump to the results. So what we found here, where these lines represent the accuracy, or in other words, the amount of information that is encoded in these vectors, we found two things. First, that French morphological features are only encoded in context. So they are only visible in the vector that's part of a sentence, but they are not encoded for the word type representation. So if we imagine that the model has a kind of a lexicon of the source language, French in this case, we found that this lexicon does not include the information about gender, number, and tense, or it includes it only to a little extent. It was quite strange to find. And then secondly, we found that semantic features like number and tense, they are encoded much better than purely grammatical features. So not all features behave equally in this context. And then we also looked at the impact of the target language and found that, the impact of target language is only visible on gender. As you can see in the case of tense and number, there's not a big difference here. Tense and number are nicely encoded in these in-context vectors. But when we look at gender, the target language does matter. So what is so special about gender? Well, gender is present to different extents. It's present in French, Italian, and German, and not in English, or only to a very, very limited extent in pronouns, for instance. It is an intrinsic property of nouns, but it also triggers agreement in other word classes, and it's often arbitrary. So there is very hard to predict, it's very hard to predict what will be the gender of French noun, for instance. So what we did here, basically, we also experiment with the modified Italian, where all the words were mapped to masculine in order to understand what was going on. And here we found that this language pair was easier to model for translation, but the gender accuracy was lower. So what does that mean? Basically, it means that the model was learning the gender only where this was strictly needed to predict the target sentence, okay? And moreover, we also found an interesting pattern, if you look here, that French-Italian has quite a lot of accuracy here, high accuracy. English has the least, and very similar to the Italian where there is no gender. And German is somewhere in the middle, which could be due to the fact that French and Italian gender, they correspond much better across languages than French and German gender do. So what did we learn from this experiment? First, NMT models can and do learn linguistic features directly from text. Secondly, the way they store this information, however, is counterintuitive. And thirdly, morphological features of the source languages seems to be learned robustly only when they are directly transferable to the target language. So somehow a mixed result, some encouraging result, but also clearly we couldn't conclude that the way these models use linguistic features make perfect sense for a human. I will quickly move to the second part unless there is a question about this. So is it okay if I finish at 5, by the way? It wasn't clear how much time I have when I start.
Yeah, it's totally fine. You're able to take all of the time that you need. Thank you.
Okay, thanks. So I will now talk about this project that started recently. And so I'm quite excited to present it to this audience. And I will try also to link to what I explained so far. So first, let me just briefly explain what this is. It's a national project funded by the Dutch Research Council, where we aim at interpreting deep learning models for text and sound, so across a wide range of applications and modes. Particularly, we are interested in the domain of text, speech, and also music. And what distinguishes a bit this project from others on interpretability is that we adopt a user-centric perspective where we try to give priority to the practical benefits for the users over only getting theoretical insights. And in the end, we want to apply the shared practices to different applications, ranging from fraud detection to music recommenders, and of course, machine translation. So first of all, the problem that we are dealing with now is defining what does it mean to have an interpretable machine translation model. So the first problem is that model explanations are not very easy to define for a sequence to sequence task, but they're easier to define for classification tasks. So I will quickly show you an example of what explanation technique looks like for instance, the case of a review sentiment classification. So imagine you could have a bunch of sentences that are extracted from movie reviews, and then you have a model, a classification model, that's trained to predict a label of positive or negative with a given probability. So this is the probability, and this is the label that gets picked up. And now we would like to get an insight on which of these words from the input have most contributed to the decision, okay? And there are already quite a bunch of techniques that allow you to do something like this, where you can see that the darkest orange words are the words that were most important to predict the specific label. So for instance, if we take the first one, this matched our intuition that best and most, they were the most important words to decide that this was a positive review. But what does it mean to explain a translation? Because when we look at a translation, we have something quite different. We have a sequence in the input and we have a sequence in the output language. What do we expect from a translation explanation? What does it even mean to look for an explanation? So one thing we could try to do, people try to do first, is to again do this kind of highlighting, importance highlighting, but for each target word. Okay, so differently for each word. The last word here will have given weights of importance here, whereas if you do it for another word, you have different weights. And if we gather them all together, we'll get kind of alignment matrix. So if you are familiar with SMT, this is something that was used to represent alignment in general. And now we'll actually get something that doesn't have just white and black boxes, but it will have continuous scores here denoting the importance of a source word for the target word choice. However, there's something missing here. First, we don't know if that's useful. And secondly, this is missing the target context, right? Because from the way I explain how this model works, we know that when the model predicts this word, it's looking at the input sentence, of course, but it's also looking at everything that came before. This is really important. So how can we merge these two sources of context together in the same visualization? Open question. And one idea that we are trying to formulate now is that instead of explaining the whole translation, because it's not very clear what that means, maybe we should focus on explaining errors instead. So assuming we can get to this type of data where we have the wrong word paired with what should have been the correct word, maybe according to a editor, maybe we should try to explain this pair instead of the whole translation as is. And this is work in progress. Another issue that we are facing is that it's really hard to predict if any of these will be useful in production. So first, it's very hard to come up with these techniques. And secondly, we don't even know that these are really going to make a difference when the machine translation or where the machine translation is deployed. So this has a bit shifted our focus of discussion to defining who specifically will be the user of this interpretability. So I can at least identify two different types of users. Of course, the researchers, which have been the main source, the main type of users of interpretability so far, for different reasons, for scientific understanding itself, to investigate the cognitive plausibility of these models, or to detect limitations and unwanted biases, and eventually design better models. So these are the goals, or some of the goals of the researchers. On the other end of the spectrum, we have end users, for instance, professional translators that post-edit NT-output. Their motivations are going to be very different. They will want to increase trust. And there we would want to increase their trust in the system. We would like to ease their user-machine interaction process and eventually speed up the post-editing process. So these are very different goals. It's important to have them in mind. So is there something that we can learn about this from research that was done before deep learning-based neural NT? And actually, yes, there is. So recently we came across this paper that's not very old, actually it's quite recent, but it was still using pre-neural SMT as the core engine. So this intelligent interface was the result of a project on NMT-assisted translation where they tried to enhance translation interface with additional, they called back then intelligible features, and these were of two kinds. They were providing word translation alternatives from the model and associated with the respective probabilities. And secondly, they were also showing related earlier translations, similar to translation memory, or taken, sorry, from a translation memory, but with additionally some highlights denoting the relation of each sentence to the current sentence. So this is what a screenshot of this interface look like. There's a bunch of information here, but quickly, so here you see the translation alternative with the probabilities, and here you see the translation memory with this extra coloring or highlighting of the words that have something in common with the current word that is being translated. So they did a lot of user studies, and they learned a lot from this experiment. So I'd like to share this with you here, because I believe it should definitely be relevant also for neural NT. And in very short, there is a elsewhere that how information is presented to the user matters as much or even more than what information is presented. And even though a lot of effort was put into interface design, perhaps more than I could put myself, these intelligible features did not improve the overall user experience. In many cases, they were found to be distracting, in fact. And these are some interesting comments from the translator that took part in this study. I don't think it is useful to know exactly how the machine translation was made. A translator can judge the quality of machine translation by him or herself. This is really, really very relevant for our work. We cannot completely ignore it, at least. Too much information becomes an obstacle. And finally, someone talking about their normal workflow. I just translate and let the system inspire me for translations while judging about the quality of suggested words myself. So I'm already doing that. Extra information would be a disruption for me rather than a help. So does it mean we should stop working on interpretability? Well, I don't think so. I think we have to do even a better job of defining who the user of this interpretability is going to be. And I realized that between researchers and users, there are actually system developers that maybe could make better use of these techniques. Their goal could be the following: to detect domain-specific errors in a specific model that has been deployed in a specific company, and secondly, trace the cause of these errors, and eventually fix them, for instance, by retraining on a specific data set. What we'd like ideally to achieve is to not just forget about the users, though, the professional translator. We want to include them in the loop, but possibly without adding extra effort and without disrupting the usual workflow. And what this could look like, at least an idea, is that we could rely on some behavioral data that we collect from them during their usual workflow. These behavioral data, together with the interpretability techniques, could be used to diagnose the problems and eventually improve them in the model by the system developers, which eventually would lead to a better neural MT models that could be deployed in a second phase. And again, work in progress. So this is the framework that we have in mind, but we have to really get to work. And I will just end with mentioning something that we are doing right now with these awesome collaborators, some of which I think are connected right now. So let's start with collecting the data that we need. This is an ongoing data collection effort that we are doing here in Groningen. And there's also focus on having a typological diverse selection of languages. That's something that I'm particularly interested with. So what we are doing, we are starting from a bunch of English documents. We have them translate by a first machine translation system, which is Google Translate. We ask the translator to post-edit it. And then we do the same thing with another machine translation system. We ask the translators to post-edit them. And then we have a third setting that's alternating with the other two, where actually the translator will just translate from scratch. I believe many of you would be familiar with such a setup. And then what we're going to do, we're going to collect all this data, post-edits, keystrokes, time measurements, questionnaires, not yet eye tracking data, but possibly this could be the next step in our project. And we do exactly the same thing with the same data and as comparable MT models as possible into these other very different target languages. And what we want to do with all this data once we're done is try to answer at least these two questions. Is NMT output equally useful for professional translation across such diverse languages? And secondly, how do post-editing patterns differ across different languages? But this data that we are collecting here will also be very useful as a testbed for our interpretability techniques. So I think I made it on time because I can now move to the conclusions. First, I have shown that neural networks are powerful and versatile models that have greatly advanced MT and other language technologies. However, the success has come at the expense of interpretability, meaning there is no bilingual lexicon to be expected, there is no source target alignment, and finally, we don't have any human readable translation rules to inspect. As a consequence, we have seen the rise of a new research field called explainable or interpretable natural language processing. Within this context, I have presented some of my work, which asks whether NMT models, broadly speaking, translate like people or not at all, but more specifically, we looked at morphological features of the source language. And the finding there was that neural MT models appear to learn linguistic features only when these are directly transferable to the target language. Then I raised this other important point that it's still not clear to us researchers what it means to explain the translation decision of a translation model. We have to face a technical challenge, which is the fact that methods designed for classification tasks are not directly applicable to MT because it is not a simple classification task, but it is sequence-to-sequence task. And there, a possible idea would be to try to explain not the whole sentence, but a specific error in a specific context. And then we have reasoned a bit about how we could make interpretability fruitful for the end user eventually. And here, well, first of all, it's really important to define the user and their goals. Secondly, there is a danger that extra information may be more distracting than useful for the translator. So this is really important to keep this in mind. And we do have a vision, which is very initial, and that consists of keeping translators in the loop, but possibly without disrupting their workflow as little as possible, and then collect behavioral data from them and merge them with the interpretability techniques to diagnose and fix problems in the neural MT. We have a long way to go to solve all of this. So we have started now from collecting, hopefully, what is the right data that we need for it, which are post-edits of neural models of which we control everything and on which we can run our interpretability techniques. And that was it. I really thank for your attention. I made it almost until 5, and I also want to give a big thank to my collaborators, which are shown here. Thanks a lot.
Thank you so much, Dr. Bisazza. I think it was a highly relevant presentation. We'd love to open the time up for questions right now, so feel free to raise your hand, unmute your mics, and also to put questions in the chat if you would.
Yeah, Michael, please.
Yeah, thank you very much. I was wondering about the notion of representation, and I'm wondering whether this representation in neural networks, whether they are actually representations. And I would think that they are perhaps not, because the notion of representation implies that it stands for something that has sharp borders. So if you talk of a tree or a table, these words have meaning and they have clear distinctions. You can clearly define what it is. And you said yourself, these so-called representation in neural networks, you don't even know what they mean. So how can you talk about a representation if you don't know what it means? I can understand there is no other word, but I think this might be perhaps one reason of the confusion, that we mix up the word, we use it in a completely different way, and it does not really make sense. So what do you think?
So thanks, it's a very good question. I have two different answers to it. One is that, well, first, it depends on how you define a representation, because I think from the point of view of the model, that is a representation, because that's the only, I really want to say representation. It's the only thing that the model sees about that word. So I don't think there's really a better word to define it, but it's very important to take it as the representation from the point of view of the model. If you intend the representation as a symbolic representation, then no, of course, it is not that. It's actually a continuous representation. But I do think the term is a good term to be used if used in the right context. If used next to linguistic representation, then no, it could really be misleading. I agree there. And then maybe embedding could be a better term, because at least it avoids.
So we have, for instance, other words. We have states. We can say we talk about internal states. And these are states,
Yeah.
but states that are non-representational. They don't represent something in the sense that they don't stand for something. But,
Yeah, but
okay.
don't you think that the embedding stands for that word, for the model? I mean, depending on where you put your point of view, from which way you look at it, for the model, that is a representation. I don't know. It's becoming a really discussion about philosophical meaning of this word.
Okay.
Maybe I'm not equipped enough to answer about this, but I think also it is being used, even it is in the name of a very important conference in machine learning, which is the Conference of Learning Representations. So it is really, it's kind of a flag word for some parts of this field. I don't think it will be abandoned soon, but I believe I agree with you that it's important to take it with a grain of salt, yeah, especially in other fields. Yeah. So I will maybe see the question that were asked. Well, thanks for your messages. Could you give a little more explanation of alignment like matrix in slide 37? So yes, I'm just thinking maybe there's a way to jump to that. Let's see. So yeah, I went very quickly on that one. So the thing is that, as I said, these models, they lack a bilingual lexicon, and they also lack a discrete alignment of source to target words, which instead was available for what's happening. Oh, sorry, do you also see something really weird?
Arianna, I could, if you would like, just go straight to slide 37.
Yes, I am not doing anything. The system is
really?
ready. I'm not touching. I was trying to find the, okay, perfect, thank you. It wasn't me doing all this funny. Okay, so basically, if I hope I got the answer, the question right. So if you see, you have this word here. I cannot, of course. So this is a target word, the insoddisfacente here, and it could correspond, for instance, to this row of the matrix, and each of the columns here is a source word. Okay, so this is source 1, this is source 2. So you, the importance score here of all the source words, this is source 1, right? And this is source 2. And then you put it here, and then you do it for, well, I should have started with the first, sorry, I should have started with target 1. And then you do the same thing for the importance scores for producing target 2, etc. And then you can collect all of this in this translation, in this matrix of scores. And then you can inspect it, and you can see at least if this looks a bit like what is an alignment matrix, and see if it matches your intuition. And it usually does, but the point with this is that it doesn't really explain the decision of the model, only in very specific cases. Then there was, sorry, there was a, Christian, you had the raised hand, sorry, I should have given you the word. Do you still want to ask your question?
No, I've actually now written it into the chat.
Okay.
So please take your time to answer the other question.
Okay.
And then.
Thank you. So what are the ramifications of the black box problem? Susie asked if you can give examples, please. I'm not sure I understand ramification as the consequences, the practical consequences, or. So I thought I gave examples of this throughout the talk. So for instance, the fact that we cannot understand why an error was made. This is, to me, a ramification. The fact that if the model has a bias to translate, this is a very common case that is mentioned nowadays. So the bias has a model to translate doctor in English into the masculine version of doctor in a language that's marked with gender, because there are these stereotypes. So there are biases in a model. It's very difficult to fix them. We understand why they're there, but it's very difficult to fix them. For instance, I don't know if the answer, I think my talk already includes quite a bit of ramifications of this problem, but if you had a different question in mind, let me know. And for Christian's question, if the first part you mentioned that morphological features are only learned if the target language maps well to the source language, I believe you tested this with an LSTM architecture. True, good catch. Do you think it would also be like this for autoregressive encoder decoder architectures like MBART? Well, first I would have to try. My intuition, yeah, it's difficult because the recurrent networks and the transformer networks, they do really use different strategies. So I wouldn't put I wouldn't bet on this. I don't have a strong intuition. But I would say the pattern could be similar because other studies have shown this, that yeah, it's true, linguistic features can be extracted from the representation or the embeddings, but they don't always match our intuition of how they are stored, how they are used. And yeah, I don't think that we would get a very different pattern for the fact that the morphological features are only learned well if the target language maps well them. Because I think this has more to do with the training data and with the task and the training objective. So the way the model is trained, it doesn't really give a concrete advantage to store this gender information, for instance, not for the specific way they're trained. And that also means in other ways that the model doesn't really need to have a deep understanding of the source sentence, but just needs to do as little as necessary to predict the right target sequence. And I would imagine that a transformer in these terms is quite similar to an LSTM architecture.
Thank you very much for the answer.
Yeah.
And one maybe follow-up question to this. You mentioned that you looked at the embedding layer, so to say, to find out whether whether it was singular or plural, for example, if I catch that correctly. Or did you also look at the different layers as well and find out in which layer this information is mostly stored?
Yeah. Our focus in that work was less on picking which layer is the best. Also, there were only 2 layers because it was a 2-stack LSTM architecture, and the focus was more on this contrast between the in context, the contextual representation, where you are informed by the by the context to generate the embedding, and instead the embedding that's stored in the embedding matrix. That's basically the lexicon or the list of word types that are known by the model. That was the main contrast that we were in. So I don't think we found a lot of difference between layer 1 or 2, but we did find a big difference between embedding and contextual representations. Yeah. Yes,
right.
Please.
Thank you very much.
Yeah, you're welcome. Yeah, there is a raised hand. Please ask your question. Lee?
Yeah. Yes, thank you to give me this chance. Yeah, you talk about this black box. There's a fundamental problem. I'm really feel puzzled. What I mean is, I know you know from the end point that you try to figure out how this black box work. But I thought that those kind of thing was all written by the code. So when they design the code, you know, how they design the code when, because when you do the code, you have all the branch out which way you to select. There is certain rule to do it. So I'm wondering,
yeah, it's very
different. What the code has to do with it.
What was your last question? I just missed it. Sorry.
What I mean is, this is a computer code should explain how those programs branch out to different directions. So finally make this selection.
So is your question, I guess, is it's hard to understand why a finite piece of programming code that has been written by an engineer.
Right. What I mean is how the engineer designed those code. Because whenever you write a program, you always you have a certain rule to follow. So that's why they come up with this.
Yeah, it has to do with the complexity of the network. So the mechanism to train is, in its core, it's very simple because it's the one that I tried to explain at the beginning. So it can be coded with actually few lines for a simple network. So if this is your network, do you remember I showed that there is this iterative process of see an error, change the weights. So actually make a prediction, look at the correct label, and use the error to change the weights. So yes, it's true, I can code this process in a few lines, but the results of this process, they cannot be enumerated. There are so many ways this model could go according to the training data that it sees. I cannot predict all the possible trajectories that it will take. And then actually, if your network is small, maybe you can, with some approximation, it's easier to understand what each of these neurons or units are picking up. But if you remember, the network is huge. It has a lot of computational units, and they are all interconnected. They are all connected. So while the mechanism itself is simple, the network is really large, and it all works in a distributed way because each unit depends on many other units. So in the practice, it's very hard to understand what's going on. I hope this gives you an intuition.
That, what you're trying to say that was from the beginning point, that the machine learning process is too complex. So you only focus on the endpoint. You just want to see from the product and try to backtrack on what happened. For me, yeah, I guess that's definitely one way to look at the things, definitely.
Yeah. I mean, thanks for it. It's good to see from another perspective. This was also everybody that started using neural network recently had this actually why something that we in principle understand mathematically leads to something that's
because
very hard
machine learning is still instructed by human. What they learn, what the information they extract from the data we feed it in is definitely
yeah, it is, but there are all these dependencies. There are dependencies between words.
I understand.
Dependencies between all these units here. Imagine we have millions of, so in a state-of-the-art transformer, we have thousands and thousands, we have millions, actually billions of these arrows, literally billions of arrows. It's
I can see that, artificial intelligence is more like a dumpster. Everybody can dump something in there.
Everybody can, sorry?
Yeah, everybody can dump something in there. And yeah, they have many.
But we don't define the weights. They are defined by the data, and they all move together. So it's a very complex system that we cannot make sense of.
Thank you for.
Yeah, you're welcome. And there is another comment by Susie. Thank you. Practical consequences are what I was trying to ask. For example, to what extent does the bias of or errors from the NMT affect translators' work? Okay, very good question. or skills, not simple post-editing work, or time and financial compensation. Well, I would say the interpretability problem, sorry, the black box problem does not immediately affect the post editor. In fact, I believe, you can correct me if I'm wrong, I would imagine that from the point of view of a translator using a cut tool, they really haven't, they might not even have perceived this change from the previous models. Maybe they notice that they are working better, but they can still be included in a similar interface and they could keep doing their work. But there are cases where the model, for instance, is behaving a very unpredictable way and it's very unreliable. So you have this case, it's called of hallucination, where the model starts to generate context in the target language, content in the target language that has nothing to do with the source language. So this is happening less nowadays, but with the first neural model, it's really a problem. Or is this still happening? You have a word in the input that is rare. I don't know, it's a term or it's a proper noun. And it gets translated to a completely different proper noun in the target language. This could not have happened with the previous models because we could check what was the bilingual lexicon that the model had learned, and we could see whether such cases were there. And most of the time they were not there. But the way machine translation, neural machine translation works is by mapping the input in this not interpretable representation or embedding, and then from there generating a target language. So there are these really strange cases. So these are cases that could directly affect a translator, I would say, because you have unreliable behavior of this model that was rare before. So maybe on average it works much better, but it's also unreliable. Whereas I think, sorry. Yeah.
Oh, sorry, I didn't mean to interrupt. I thought you were finished.
I am finished. Go ahead.
Okay. Well, I think that might be all of the questions for now, and we're really grateful for all of the discussion that's been generated, and we're especially grateful to you, Dr. Bisazza. It looks like there might be one more question if you'll allow it.
Yeah, it's okay. Hopefully not too long one.
If it's possible, can you hear me?
Yes, I can.
Excellent. Well, thank you very much. Well, this is Bart from the University of Vienna, and I've been very much an advocate of explainable life for quite some time, and working on it, and actually applying for a project at the moment. So I'm very much interested in the progress of your project. And the first small question, first of all, will these slides be available in some point? So maybe you can get back to it with questions. Will they be available publicly?
I don't know where they could be available, but I will coordinate with organizers if they can be made available. Yeah.
Okay.
Yeah, I'm fine with it.
The talk will be made available online. We have a channel.
Okay, the recording you mean? Yeah.
Yes.
Okay, that's fantastic. Well, thank you very much. Maybe we can keep in touch in the future.
Yeah, just send me an email. I would be happy if you have a follow-up question. Feel free to send it. Yeah.
Thank you very much.
Yeah, you're welcome.
All right. Thank you so much, Dr. Bisazza. We're very grateful that you were able to give this talk at the CRITT Translation Colloquium, and we would love to see you and everyone else here at the next Translation Colloquium.
Okay, thank you. Thanks to all of you that have participated in the discussion, and thanks for your attention. If you have a follow-up question, please email me, because the chat here, I will not have access to it. I think I received a question, but I don't have time to answer it. So just email it to me and I'll be happy to take it. Thanks a lot to all of you for having me.